So now we'll start the session. In the last class, we have discussed and concluded with the single phase follower controlled midpoint rectifier as it has been shown here. The circuitry is here. So as you can see here, the circuit is very simple. Only now we are using two thyristors connected in the secondary of the transformer. So 1:1 transformer is used as it is indicated by the two dots which are symmetrically arranged on either side of the primary and secondary of the transformer. So 1:1 transformer normally we are using to couple the input AC supply as it is to the secondary. So we got here 3 points. A is there, N that will indicate the midpoint where we are going to connect in between the midpoint and here the load, resistive load. At point A and B, two thyristors T1 and T2 are connected. So rest now we can apply the AC input. So the heading is single phase full wave controlled midpoint rectifier. Although it is a rectifier, it is going to convert your AC input to the DC. Okay. So just once again briefly we'll see what is happening here during both the cycles, positive and negative cycles. E equal to EM sin omega t AC supply you are applying here. Same thing will be coupled as it is to the secondary because of 1:1 transformer winding ratio. Now during the positive half cycle, so this A will become positive with respect to B. This point A will become positive with respect to B. So because of this, as A is now become positive, it will be connected to the anode of T1. That will turn on the T1. Similarly, B is becoming negative. Hello? Hello? Okay. Similarly, B becomes negative, that is connected to the anode of T2, will turn off the T2. Means during positive half cycle, T1 is coming into picture, not T2. Means T2 is turned off, T1 is about to turn on. Now during this instant, you can just consider this as alpha here, okay. So better we can understand here. This is the first firing angle where we are about to apply. Still we have not yet applied. So 0 to alpha during this period, your T1 is in the forward blocking state. So our forward voltage what we applied between A and B is not sufficient to take on this T1 in the conduction state. So that's why it is in the forward blocking state. So this will be changing from forward blocking to the conduction state when you apply the triggering pulse at phase angle alpha. Up to this instant, 0 to alpha, your T1 is in the forward blocking state, therefore it is turned off. So whatever the input it is coming at the secondary, the same thing is applied at the thyristor T1 because it is turned off. So hence no current is flowing, hence no load voltage or no load current. Is it clear? So once apply the firing pulse at angle alpha, okay, at the gate of the T1. Now T1 will be turned on at the instant omega t equal to alpha. So you can see the firing pulse is applied at alpha. Suddenly the T1 will start conducting, and whatever the load voltage which was appearing across T1, which was open circuited during 0 to alpha, now will start appearing across the load. Means whatever the load voltage, whatever the input voltage is there, which was happening across T1 during this period, now it will be shifted across the load because of the conduction of T1. This is how you need to understand and explain the things here. Now this will continue as up to phase angle pi. Okay, you can see with the hash line it has been shown T1 is conducting from alpha to pi. Alpha where you applied the firing pulse till pi where your AC input is going to reach the 0. During this instant from alpha to pi your T1 is going to conduct. Hence load voltage has been shown here. Similarly the load current is also going to follow the voltage. But during this instant the voltage across T1 will be reduced to the cutoff voltage, that is very slow, or ideally it will be 0. So that's why it has been shown here negligible voltage across T1, that is T1 is on. Now at pi, naturally the input is becoming 0, that will turn off your T1. Okay, now we'll enter into the negative half cycle. During negative half cycle, you can see A becomes negative, that is connected to anode, that's why it becomes turn off. Now B became positive, that will be connected to the positive of T2, will turn on the T2. Now T2 will be suddenly turned on at the instant pi. At this instant you can see. Okay. Now T2 will not be in the conduction state as long as we apply another firing angle at pi plus alpha. You can see. This is the second firing angle. If the firing angle apply modutana, T2 will never be in the conduction state, but it will be in the forward blocking state. That too in the negative half cycle. Okay. So that's why you can see in this instant, that is from pi to pi plus alpha, in this instant, negative half cycle, T2 of course it is coming into picture, but it is in the forward blocking state. That's why whatever the input we are getting, all the thing is happening across T2. Across T2. Once we apply the firing angle at pi plus alpha, we'll turn on the T2 and whatever the voltage drop is happening, was happening across T2. Now it will be shifted. You can see it will be shifted from here to this one. Means T2 will start connecting from pi plus alpha to 2 pi. So we need two firing angles here, one during positive half cycle, another one during negative half cycle. Now you can see the direction of the currents here. When T1 is conducting, the current was flowing in the clockwise direction, but when T2 is conducting in the negative half cycle, the current direction was exactly opposite. But you can see the direction of current through the load will be same, right to left only. Okay. So these things you should highlight when you are going to explain your operation. Now coming to the derivations here. So normally in the examination along with operation, derivations are normally asked. Once again the kind of derivations what we did for single phase half wave controlled rectifier with R and RL loads or flywheel, the similar steps we'll have to follow here. All those steps I will not show here every time. So you can see here I have just taken from alpha to pi here. So for your understanding purpose, just I want to tell. So you have to consider one full cycle. During positive half cycle, your T1 is conducting only from alpha to pi. During negative half cycle, your T2 is conducting from alpha plus pi to 2 pi. So these things you have to write here in the beginning. When you resolve them and simplify it, you will be getting this equation. Are you getting this point? So this I hope we did during the single phase half wave control rectifier. So you start with considering 0 to 2 pi. Okay, the integration in it, you have to divide. You write it as 1 by 2 pi inside the bracket. You take 0 to alpha. 0 to alpha andre enu irangilla load voltage, that you won't consider. You just consider from alpha to pi integral, that is em sin omega t dt, plus during negative half cycle ಎಲ್ಲ ಕಂಡಕ್ಟ್ ಆಗ್ತೈತೆ pi to pi plus alpha conduction ಇರಂಗಿಲ್ಲ, load voltage ಏನು ಇರಂಗಿಲ್ಲ. Load voltage is there only from pi plus alpha to 2 pi. Means you have to write before this one 1 by 2 pi It is not written here. If you want to just note it down one step before this. Are you with me? Just to note down this one before this one if you want. Before this one, you have to write 1 by 2 pi inside the bracket. So one is integral from alpha to pi em sin omega t dt. That is, this one is, we are writing this term because of the positive half cycle, this load voltage we are getting. During negative half cycle, this load voltage we are happening during the T2 is conducting. That is, the range is from integral from alpha plus pi. This is alpha plus pi to 2 pi. Okay. So if you simplify this once again, we are going to get this one 1 by 2 pi, because in the outside bracket another 1 by 2 pi. So alpha plus pi to 2 pi, it will be similar to the alpha to pi. So if you apply the trigonometric rules there, so those two terms, 2 will write 2 em sin omega t dt, and 1 by 2 pi that 2 and this 2 will got cancelled, and you will be getting this one. That is, EDC equal to 1 by pi integral from alpha to pi em sin omega t dt d omega t. Is it clear, guys? Any doubt here? Just tell me. I'll just repeat those steps in the wordings only, because it is not written here, and I hope you know these things, basic things. Anything else you want to ask? Shall I continue?
Yes, sir.
Okay, no problem. If some of you are getting the doubts, you need to work out this one with the pen and paper. Later also you can work out, and this you keep with snapshot. Send me WhatsApp group if you are not getting that one. I will solve in paper and reply to that. Next one, you simplify this one. You simply by applying the trigonometric rules here. EDC equal to EM is a constant. You keep it outside. So because this is the integration only with respect to omega t. So depending variable sin omega t only will be kept inside the integral. So integration of sin omega t will be minus cos omega t, applying the limits from alpha to pi. You apply this one, you will be getting this one. And again, by varying the phase angle, we can see from alpha to pi, we will be getting the minimum and the maximum values for the average or DC voltages. And if we simply divide this by R, okay, we will be getting the current here, average load current or DC current. So can anyone tell me that what is EM here? Suppose in the problem, normally we are giving AC supply here. Okay. So AC supply means E is given. How will you be getting EM from AC supply? Suppose if I will say in the problem AC supply is 230 volt. What is EM value? Can anyone tell me? Or EDC? EDC will get by this formula. EDC we are getting from this formula, that is EDC equal to EM by pi. It is there. EM is not the exactly the AC supply what we are giving 230 volt. It is something else. What is EM here? Can anyone reply? Because the such what
Peak voltage.
yeah. Who is this? Yeah. You can tell anybody has start.
Peak voltage.
Yes, pardon. Pardon.
Peak voltage, sir.
No. Sorry.
ERMS by root 2, sir.
ERMS is not given, dear student. ERMS is not given. This is the AC supply. Hope these such kind of problems you are doing since from first year in the basic electronics. So that thing you can see, because some of you, I have seen that because such problem is given in the first CI. AC supply is given, and okay, some, shall I go with some previous year? This problem I have asked in the CI one. Is it this one? No? Can anyone tell me? The problem I have asked in the CI one. And if you go through all these problems, whatever slides I have shown, here you can see, for your knowledge, I am just showing this one. So half a controlled, here it is given. is not taking EM as it is. So RMS secondary voltage will be taking EM by root 2, but what is EM we have to see. Can anyone reply? At least know what is EM. This is, you can see here, ED is equal to 0.24 times EM we got in single phase of a control rectifier. You just once again go through these things. You may be having the doubt here. I want you to work out this one so that that will be clear. It is very useful in solving the problems. So I don't think EM will be taken as it is. So it may be root 2 times of that. Maybe you are taking. Is it correct? Root 2 times of that we are taking. Anybody is confidently tell. Okay, this is the derivation part. Let me complete this. Then during numerical part, just I want you to go through the numericals and you will come to know such kind of difficulties. Next one, RMS load voltage derivation is there. So that is a root, that is 1 by 2 is it is given the power. That is a square root. Mean means 1 by pi average you are taking. Root mean, root and mean. Square, the square of the input AC you have to consider here. Again you will be getting the alpha to pi. Directly we will take it because not necessary, because once we already did when we are getting this step. Once if you do it, that is sufficient. Suppose if he is directly asking you to derive RMS load voltage derivation, but in that case you need to do it. If he is asking in the bulk that to do the derivation for EDC, ERMS, everything, in the beginning only, once if you do it, somewhere once you have to show it. Then just directly you can continue with this one. That is alpha to pi EM square sin square omega t d omega t. Now the constant thing you keep it outside, that is EM square. Square root, it will become outside of that will become EM only. EM square, that square root will got cancelled, EM will be coming outside. Inside of bracket, what we left out is 1 by pi. So integral of sin square omega t is 1 minus cos 2 omega t by 2. So hope you know this formula, that is cos 2 omega t equal to cos square omega t minus sin square omega t. Okay, or 1 minus 2 sin square omega t. So if you apply that formula, you will be getting this one. So again 1 by this 2 is there. So if you simplify this one, the steps have been shown here. So what we are getting inside the bracket, 1 by 2 pi is coming outside. And here you can see how he is going to divide. So divided by 2 is going to happen to each term here. 1 by 2 will be getting separately. Cos 2 omega 2 by 2 also getting separately. So 1 by 2 is a constant. Separately you apply the integration, that will keep it outside. So we will be left with only omega t, because integral of constant is omega 2. Integral of cos 2 omega t is sin 2 omega t by 2. Okay, is it clear? Now we will apply the limits alpha to pi. So once you apply the limits and simplify like this as it has been shown in the steps, so finally we are getting or arriving at this expression for the ERMS. So one thing you have to understand here, derivation is important, but also equally try to compare the expression what you got for full wave ERMS and half wave ERMS. In half wave ERMS case, here we got 8. In EDC also, in half wave ERMS, we got it as only cos alpha. 1 plus cos alpha means 1 plus is added, means it is going to increase your efficiency. Rectification efficiency, here it is indicating that it is increasing simply by adding one additional thyristor here. Okay. So this is the final ERMS expression we are getting. So before we go with this inductive load also, we are going to include this one. So if you want to ask anything, you can ask. Anybody? We'll take pause for a few seconds and some room for you to talk. Before we will continue with this, another very important one to be discussed. RL2. So don't confuse with these here, these signs here, plus minus I am showing. This I am showing because of the center tab, that is a midpoint connection, it has been shown here. It is just indicating that the couplings, whatever it is happening from primary to secondary, are equally happening. Maybe equal, they are equal in magnitude, but polarity may be same or different. That will see. Because in the previous one we have seen, no, in the current here it is from clockwise and here it is from anti-clockwise. Clockwise and anti-clockwise will change the polarity, but the amount of current flowing through the load will be same. Okay, anybody want to talk? Just to be a little bit interactive also. Before we continue with the other load. Shall I continue?
Yes, sir.
Does anybody want to ask? Okay, let's continue with this one. Nobody is interested to respond here. So we'll assume that everything is okay. Later, if you get any doubts, you can see the video. Any video will be kept in recording mode. That I will rectify and upload it later. So next one we can see a very important point here, a single phase full wave controlled midpoint rectifier with RL load. R load we have seen. Now load that is a inductive load will be coming in series with R. First of all, circuit diagram not colorful. Colorful I used here just for you to explain it. For convenience purpose I used here. So there only you will be drawing a black and white only. The black pen you need to practice. Okay. So first to draw the circuit diagram, simple and neat circuit diagram. And taking the reference of circuit diagram, that is as shown in the figure, like that. Just I will explain here, listen here carefully. Figure shows a simple circuit diagram for the single phase full wave controlled midpoint rectifier with RL load. As shown in the figure, you take some figure reference here, as shown figure 1A or 1B or something like that. As shown in the figure XX, supply voltage VAC is applied at the primary of the transformer. The secondary of the transformer is midpoint connected with the load R and L in series connected between the point midpoint N, and here we name some point, for example midpoint N and at this point you can name some point. Two thyristors T1 and T2 are connected in the full wave controlled rectifier mode. Anode of T1 is connected to point A and the anode of T2 is connected to point B of the secondary of transformer. Only this much you need to explain. Another important point what I want to tell, because of the midpoint connection, there are two voltages across the secondary of the transformer. One is denoted as VAN, happening between the points A and midpoint N. Another one between the points B, that is the lower point P, and midpoint N, denoted by VBN. VAN concerned with the thyristor T1 when it is on, and VBN concerned with the thyristor T2 when it is on. That's all. Andre ಏನು ಮಾಡಬೇಕಂದ್ರೆ, so when you are explaining the structure of the circuit, so simply don't tell only the structure of the circuit. Andre ಯಾವ component ಅದಾವ ಎಲ್ಲೆಲ್ಲ ಅದಾವ, okay, you will explain about that. But next what you are going to explain is operation. ಅದಕ್ಕೆ ಲಿಂಕ್ ಕೊಡುವಾಗ structure explanation ಮುಗಿಕ್ಕಿಂತ ಮುಂಚೆ you should tell that like this, how you will provide the link between the structure that you are concluding and next operation you start ಮಾಡ್ತಿರ್ತೀರಿ ಹಂಗಂದ್ರೆ. So VAN is the voltage concerned with the T1 when it is on. VBN is the voltage concerned with thyristor T2 when it is on. It means that, so in the next operation case we are going to extend that only one thyristor will be on in each of the half cycle. That already we know it. But that part we are going to explain during the operation. This is how we are giving some touch to the, we are telling to the evaluator that next she is or he is going to start explaining the operation next. Like that. So next, for the submitting operation, next how we'll see. So if the waveforms are there, neat waveforms are there here. So we'll come back to this these waveforms. First let me explain the basic things here, skeleton of your operation. So operation will be similar to that of the single phase fully wave controlled multi-point rectifier with R load only. Only L is coming into the picture. So because of L only, let me show you trailer here. Some notch you are getting that during positive cycle in T1 conduct ಆಗ್ತಿರ್ತೈತಿ, it will continue to conduct. It will natural commutation because of this inductance flow. Because we already learned in last few videos also in the flywheel diode. That's why we are using to avoid this half notch. We are getting the negative half cycle. So let us see why we are getting this negative. So don't, once again I want to tell you that don't go with these polarities, positive, negative, what I have shown here. You be with these polarities, what I have shown in this slide, these things. Okay. During positive half cycle, A will become positive, T1 will be on. During negative half cycle, T2 will be on and current will flowing like this. Only this much you keep in mind so that it will become very easy for you to understand the operation. Okay, come to this one. So during positive half cycle, here you can see AC signal we are applying, VS is applied here at the primary of the transformer. So we can start explaining the operation. Let me start from the beginning here. As shown in the figure 1 and 2, AC input VS equal to Vm sin omega t is applied to the primary of the transformer. This is a sinusoidal waveform as shown in the figure 2. That is, figure 2 is a waveform. Basically, the operation now consists of two parts. Means we have to explain now next during positive half cycle what will happen and during negative half cycle what will happen. So during positive half cycle, this upper winding is there, no? That is coming into picture. Okay, because during positive half cycle, point A will be positive with respect to point B. Once again, I am telling you, don't consider these plus minus. Okay, they are simply indicating the voltage polarities of the two equally divided secondary voltages, VAN and VBN, that already explained in the construction part. Now during positive half cycle, as A is positive with respect to B, will turn on the T1 and will turn off the T2. So therefore, during positive half cycle, from 0 to alpha, because we not yet applied triggering pulse to the gate of T1. Till that, T1 is in the forward blocking state and T2 is totally turned off. Means it is not coming into picture. It is not coming into picture very better for your understanding. Okay, this is not there in the picture. Only T1 is there in the picture. Okay. Now T1 is about to turn on. Yava turn on agtate? Only when we will apply the triggering pulse at alpha. Alitana namdidu off air. Ill negative hash bandetla. This is the full wave control rectifier, guys. The full wave positive and negative, negative and positive and negative bartane irthe. Idu hindindu. The T2 was conducting. T2 conduct ಮಾಡಲಾಗ್ತಿತ್ತು. ಅದೇ ಇಲ್ಲಿ ಕಂಟಿನ್ಯೂ ಆಗಿದೆ. means but T1 positive half cycle na ಬಂದ ಮೇಲೂ for blocking state ನಾಗೆ ಇರುತ್ತೆ ಎಲ್ಲಿ ತನ ಆಫ್ ಸ್ಟೇಟ್ ನಾಗ ಇರ್ತೈತಿ ಎಲ್ಲಿ ತನ ನೀವು ಅಪ್ಲೈ ದಿ ಟ್ರಿಗರಿಂಗ್ ಪಲ್ಸ್ ಬಟ್ ಯು ಅಪ್ಲೈ ಟ್ರಿಗರಿಂಗ್ ಪಲ್ಸ್ ಓನ್ಲಿ ಅಟ್ ಅಲ್ಫಾ ಅಲ್ಲಿ ತನ T2 ಏನು ಮೊದಲೇನು ಆನ್ ಇರ್ತಲ್ಲ ಅದು ಕಂಟಿನ್ಯೂ ಆಗಿ ತಿಳಿ ತೋರಿಸುತ್ತೆ ಓಕೆ ನಾವು Now what is happening here is that 0 to alpha, that's what this negative has mentioned. Is it clear? During 0 to alpha, output voltage, what we are getting, it is because of the negative, that is the T2 was conducted. Okay. T1 is in the forward blocking state, still we have to apply the triggering pulse to the gate. Okay. So that's why it has been shown here, T2 is there. Okay. Now we can see two more waveforms I am showing here, voltage across T1. As T1 is not yet conducting, the voltage across it is slowly increasing by this amount of 2 Vm sin alpha. Okay. So because we are yet to apply the triggering pulse at alpha, omega t equal to alpha. Omega t equal to omega t badly you replace it by alpha. That is 2 Vm sin alpha. So this much amount of voltage is happening across T1 when it is in the forward blocking state. But voltage across T2, because T2 is off, so no voltage is happening. There is this part, this winding part is not coming into picture. That's what is called a midpoint. Midpoint means totally isolating between these two upper half and lower half circuit operations. This is keep in mind. During positive half cycle, only this loop is coming into picture, upper loop. T1 is conducting, forward blocking ಒಳಗೆ ಏನಾಗ್ತೈತೆ ಬರೀರಿ, forward conduction ಒಳಗೆ ಏನಾಗ್ತೈತೆ ಬರೀರಿ, ಅಷ್ಟು ಮುಗಿತು. During negative half cycle ಒಳಗೆ forward blocking ಒಳಗೆ ಏನಾಗ್ತೈತಿ, forward conduction ಒಳಗೆ ಏನಾಗ್ತೈತಿ, that you have to explain. Both the upper and lower half operations are totally isolated by this midpoint connection. That's what is called midpoint or center tapped. You are tapping it. Okay. So now you can see what is happening when once you apply the triggering pulse at omega t equal to alpha. Once you apply the triggering pulse at omega t equal to alpha, your T1 will be turned on, it will be short circuited, okay, and will start conducting the current. It will start conducting the current like this. The current direction has been shown. This circuitry I have shown specifically for the what is happening during positive half cycle. And voltage across R and L will start happening. And this current is main responsible for the storage of energy in the inductance in this direction. Current will start storing in the inductance. Okay. So this is happening, the storage of current is happening in the inductance for the whole positive half cycle, that is from alpha to pi only. So this it has been shown here, T1 is conducting from alpha to pi. Pi ನಂತರ next ತೋರಿಸೇನು because at pi will reach 0, input will reach 0, natural commutation ಆಗಬೇಕಾಯಿತು, but it is not happening because of the stored energy in the inductance will not be released immediately. ಅದು empty ಆಗುತ್ತಾನು current flow ಆಗೈತಿರ್ತದೆ. Okay, even though we entered in the negative half cycle, natural commutation is happening, but this energy stored in the inductance is not allowing that one. Means it is dragging your conduction of T1 still more further, that is up to pi plus alpha until you will apply the next triggering pulse to the T2. As soon as you enter at pi, the negative half cycle, T2 or lower half of the circuit is coming into picture, but still some current was flowing in the upper half, like this it has been shown. That's why we have shown the conduction of current is happening through T1 or upper half circuit from alpha to pi plus alpha. So that's why voltage across T1 will be remaining almost negligible or cutoff voltage from alpha to pi plus alpha. And but as T2 is off, you can see voltage across T2 will be like this. This much amount of voltage is happening. Now what is happening during negative half cycle, you can see when you apply the triggering pulse at pi plus alpha during negative half cycle, the lower half of circuit is coming to picture T2 will be turned on. Once T2 is turned on, like this, the current will start flowing in the anti-clockwise direction, like this. Again, we'll be getting, that's why it has been shown VBN voltage. VBN voltage is now coming to picture. VBN is nothing but exactly opposite to that of VAN. They are equal in magnitude but opposite in polarity. We can take VAN as equal to minus VBN. Okay. So VBN is appearing like this because we have all the thing operation is happening during negative cycle. That's why we are considering it as VAN equal to minus VBN. Again, this T2 is going to conduct from pi plus alpha to 2 pi, and it is again extending that hatch now we are getting here. The next cycle which is about to begin here. So that's why you got this hatch because of the conduction of T2. Means we are going to wind up the negative half cycle operation with the hatch what we are getting in the period from 2 pi to here alpha, where we are going to apply the triggering pulse in the next cycle. So this is how, guys, we are going to get we need to explain about the operation. Again, as shown in the waveforms here during negative half cycle, as T1 is off, most of the output voltage is happening across T2, but as T2 is conducting, only cutoff voltage is appearing across T2 like this. So T1, T2, T1, T2, like that it is continuing. But how to remove this negative hash? So we have to provide, so we'll make somehow that inductance should immediately release whatever the energy stored in it by providing some short circuit path. So that can be done by using this, by connecting some diode here. But here I will show here. Here you can see. So during negative half cycle, we are going to make this diode to conduct. It will short circuit your inductance, and it is going to allow the path for this energy stored in the inductance to discharge, so that hash you can see now will be removed. Okay, this is the effect of a freewheeling diode. Okay. So one more thing I want to add, how we can explain, because we can vary the firing angle here. At particular angle we are going to trigger both T1 and T2. If you trigger both the SCRs at alpha equal to 30, I have shown here clearly. You have to indicate at alpha equal to 30, your T2 was conducting. Now our remaining angle T1 is conducting, again T2, and then it is continuing. Similarly, they may deliberately ask you to explain a single phase fully controlled rectifier with RL or R load at specified phase angle. Maybe alpha equal to 30 I have shown here. You can just indicate that it is alpha equal to 30. But big difference will occur at alpha equal to 90 degree. Because exactly at midpoint of the half cycles, you will start conducting alternative thyristors, T1, T2, like that. This one thing you should remember about the single phase midpoint control rectifier with RL or R load at alpha equal to 90 degree. So this how here I have shown how we are going to remove the negative hash what we got. So this one during the each cycle with the help of this flywheel diode here. This diode simply what it is doing during negative half cycle, it will be short circuited, and it is going to provide the shortest path for the energy stored in the inductance to be emptied, so that in the next cycle our T1 will come into picture. It is load output voltage will come into picture continuously without any gap here. So here you can see, so the path has been shown here, how the current is flowing here. The energy stored in the inductance start discharging like this. Some ground we can connect here to start discharging through T1, R, L, DF, and some ground we can show here. Normally we have to show here. Then it will be discharged. Because of this one, as DF is conducting here, so this much amount of time will be taken to discharge whatever the energy stored in the inductance with the help of DF. There is a flywheeling diode. DF means flywheeling diode. These are some of the derivations are there. Similar tips you can follow. You can work out them at home. You can also refer to the study material uploaded. or notes or textbooks, you will come to know about these things. Some numerical it has been shown here. So find EDC, ERMS, IDC and power delivered to the resistive load having 10 ohm, the single phase whole wave controlled bridge rectifier 230 volts and SCR triggered at 60 degree. He is asking you to find out EDC. This formula you can use. IDC simply you divide it by R, that is 10 ohm, and ERMS you will supposed to use this one. Substitute the given data directly here, you will get the answers. So anybody want to ask? Chopper will be going to see in the next class here. So today we covered two important points here. Single phase full wave controlled mid-point rectifier with R load, just to be brief about that one. RL load, that rectifiers we are getting, and that can be removed with the help of freewheeling diode, and some derivations also we have seen. Yes, okay. Anybody want to ask anything before we'll wind up the session? Yes, anybody want to ask?
No, sir.